My name is Grebennikov Roman, and I'm going to talk about biases, but not really ethical biases, but more like a behavioral biases. It works. So that's me. I fix it. I need to point to the laptop. If I do it like this, oh, it works. Okay, so I'm coming originally from academia, did some different areas of machine learning, but for the last couple of years I'm working in search and recommendations and with focus on relevancy and ranking. And right now I'm working on an open source project which is called Metarank, which is like a learn to rank thing for mere mortals. And when you're working on the ranking and coming from e-commerce, you're focusing on a different aspect of biases. So when you're applying machine learning to humans, yes, you need to think about ethics and so on. But if you're doing it for products, maybe for some dishwasher or for a group on LinkedIn or a cat video, there is not that many ethical biases you might have. So that's another wonderful thing on working on e-commerce. So these are use cases for ranking, and ranking is around us where you have a list of something and you have some sort of an end goal to optimize. And the most common approach I've seen in different companies, just like a YOLO thing, just sort everything by the number of clicks you have or by the number of page views or whatever. And then it's quite easy to implement. It seems that like, hey, these things which are getting a lot of clicks will get even more clicks. But there are some pros and cons on this approach, and probably you will introduce, what a surprise, a bias. So items with more clicks will get even more clicks, like in capitalism, richer getting richer. And people are having some sort of behavioral biases, and they don't just go too much on the bottom of the list, but because they are lazy, and your new items are not going to make into the top first page of your search results because they just have less clicks and they don't have even a chance to get more clicks because they are not entering the first page of search results ever. There are multiple types of biases you can see in e-commerce or in some other areas which are not related to scoring and ranking people. So the first one is position bias, which is probably the one people starting to work with when they focus on biases. And usually it's the strongest one out of the whole list. There are some presentation biases when the way you present something to people affects the way they behave. Some context biases, maybe model bias when you train a machine learning model of an output of this model and you just go like a Ouroboros eating your own tail and degrading the whole experience. So we'll focus mostly on the position bias, but all of them are kind of similar from technical perspective and what you can do with them. So I personally click on first items on the list because I'm just lazy. I don't have enough time to scroll through the whole listing. But from the relevancy engineer perspective, you got a click on the first position on your search results or on recommendations or whatever. Was it done because it's relevant or because it's first? So how can you distinguish? Is it a good signal or it's just a noise? Because you always observe it together. So we did some sort of an experiment for this particular talk. So we made a movie search movie search ranking dataset with Toloka AI. Kudos for folks from Toloka for helping us to make it, because without their help, I will probably fail spectacularly. So we took top 10,000 movies from TeamDB database with titles and all that stuff. You can see the example how it looks like for the internal structure. And we used a Google keyword planner tool to fetch all the search queries, which are usually related to these movies. So there is some sort of an API you can interact and pull this list of all the queries, which you can see it's quite small here, but you can see that for the metrics, there are Wachowskis, Animatrix, Glitch in the Matrix, and so other. People are searching together with this movie. And we did some sort of labeling through the people working on Toloka, so it was approximately 700 something labels, and 8% of them are relevant. So what we did is actually presented a query, a search results like this. Toloka actually has a proper search relevancy template if you want to do this thing for your company, and it is unbiased. So that's how it looks like on the left. So you have a product and a query, and you can say, is it relevant or not? There is no information about position, so it's just a yes or no answer. For us, we wanted to shoot ourselves in the foot, so it's instead of that doing it properly, we showed something with explicit item ordering. And then, by doing an explicit item ordering in this list, we introduced a position bias there, but with a trick. So the search results were not ranked by the text relevancy by BM25, but they were just top something relevant, but shuffled. So the position of the probably relevant movie was somewhere, and it was independent from relevancy. So you might expect that your this graph of probability by position should be like a flat. So because a relevant movie can be anywhere, you shuffle the results, but still people are clicking more frequently on top items and then on the bottom items because just they're too lazy to scroll. We did some data cleaning, and the way you can clean it is still the same. So it's from my observation, because not all the queries are very exact, so it can be quite inexact, or just with multiple search results matching for your query, and you're just more often clicking on the top matching results than on bottom matching results, because just position bias. That's because we're people. It's not only about position. So if you represent something in a grid, you expect that people scan it from left to right, from top to bottom, if they read from left to right, from top to bottom. But usually it's some sort of, can be in a very obscure way. And due to this obscure way, you might notice that this item, like number 5, might get more clicks than the item number 4, just because it's below. And people are scanning search results in this way. And for the presentation bias in this particular data set, what we also observed, so there is a segment of desktop users with 3 columns on the search results with the different types of layouts. So if you go for the data set, I will give you a link later. You can see that there is some like a drop after an item number 3 here, like the first row, you can see it instantly, and then something else. And if you have multiple search results which are relevant to your query, you might just say, okay, that's it. I don't want to go down to the list because I already found it. And for my own observation is that bias in search depends on the function of your search or of your recommendations. Is that for this particular case of movie search, all the queries were very precise, and this kind of a navigational queries. You already know what you're looking for. You're looking for the matrix, you're looking for your cat food. And if you're looking for cat food, it doesn't really matter on which position your favorite cat food is ranked, you will just find it and buy. And if you're doing a discovery thing, you have no idea what you're looking for. Like you went on Zalando, typed jeans, there are 20,000 different jeans, and you won't be able to scroll even for the first 5 pages. You will just go from up to down, first 5, and call it a day. So in practice, if you're trying to mitigate bias or de-bias it, it's kind of complicated because you're rarely observing it separately from the relevancy. You observe it together. So it's the same data set, but we just not shuffled it, but sorted by the text relevancy, by BM25. And you can see that, okay, the results which should be ranked first, it's usually clicked more frequently because there is probably a correlation, high correlation because between the text relevancy and the click probability. That's the point of the search. But not always. So from the perspective of a relevancy engineer, a person working with the ranking, the whole problem of optimizing your ranking is just, if you're not really comfortable with things like learn to rank and lambda mart, with just a short introduction of this idea of ranking, is that it's just like a classic. So you have an implicit feedback coming from your users. You have a query, the user was presented this list of results, the user clicked on the item 3, and we assume that this item is relevant to the query because user decided that it's relevant. That's noisy, there is a lot of subjective information there, but still you can have this data almost for free, and you can do something about that. You can use item metadata as ranking factors. If you are in e-commerce, it can be price or maybe text relevancy information between the title of item and between the search query. And you use a very specific loss function. So in classical machine learning, its loss function is not sensitive to the position of the item. But if we're working with ranking, you might feel that the error made on the beginning of the list is not the same as error made on the end of the list. So for example, you swap first and second search results. Will it matter much? Not really, because it's almost the same. But what if you swap first and last? Yes, probably it will matter, because your overall search experience will degrade because there is an irrelevant item on the top. So there are some different types of loss functions, and they are pair-wise, so it's more about a pair of items in your ranking. And the most popular is in DCG, which are we going to talk about and mention a bit. And not all clicks are made equal. So from the lambda mart perspective, you can, from the learn to rank perspective, all your information about the implicit feedback is unfolded into some sort of a tabular data. So, okay, we were presented with these 4 items. We have all this information about the ranking, and we know that first items were examined but not clicked, and the third one is clicked, so we can assume that it's like a positive and negative labels. But observing this thing from this relevancy perspective, you might and all our feedback information. So we know that the click happened on the first position is not the same as click happened on the third position. And so they are like affected by bias. And if we can estimate bias, like here, we have some sort of observed relevancy and we can just weight it by the bias. So we know that click on the first position is highly affected. We know how high it is, how strong is this influence of bias, and we just offset the importance of this click a bit lower. So, but the only thing we need to do is just to estimate this type of bias. There are different approaches to do this, but the most probably old and popular one is called inverse propensity weighting. So you shuffle a short segment of your traffic and see how people interact with the same product within the same context, but on a different position. So just an example from this paper is that's how people usually click on different positions in general, like click-through rate per position. So everyone is clicking somewhere at the beginning. But the second one is click-through rate of the same item within the same context, but just on a different position. So it's the same search query, the same search results, the same product, but just on a first position, it gets much more clicks than on a 15th position because of this position bias. But if you shuffle it, you can reconstruct this information about how strong bias is per position and then just offset by it. So that's how it looks like with the same socks, same query, different position and different amount of clicks because of the position bias. The product is the same, you aggregate it per product, per queries, and then you will get some sort of decaying graph of bias, and you just weight it and call it a day. Will it work? Probably yes, but the problem is that shuffling affects your business metrics. So that's a slide from Mises conference, and like this shuffling of search results gives like a significant drop in conversion and average order value. So at the end, this experiment can be quite costly. So it's not like you are paying for that, you're just getting less sales, and it might be quite expensive to do this experiment. There are different ways to make it less costly and not just shuffle everything, but shuffle top 3, for example, items, because they are most heavily affected by bias. So we don't need to shuffle everything, we just need to shuffle something on the top. You can do not the complete shuffling of small segment of traffic, but just swaps of items in the whole traffic. Or if you're running multiple A/B tests, you can just exploit it as is. So you don't need to shuffle, you already have it happening organically due to different A/B test ranking models you have. So the same items within the same context are still ranked on different positions. Not because of you are shuffling the traffic, but because of some other reasons, and you do some other experiments. But we can go further. Why it's 2023 almost, and we're using statistics to estimate bias. Why don't we just use a machine learning model to estimate this type of bias? So technically, bias is trying to estimate this bias. You need just to predict the click probability on different positions based on only biased factors. Like you're trying to predict probability based on item position, item cost, item popularity, but without any context on the ranking you have. So in the perfect, if you use only the position as this factor, you will just converge to the inverse propensity weighting actually, but you can mix together some other factors which are not leaking the context inside of this machine learning model. So you can do this to predict the bias, but what can you do with this prediction? As we suggested, you might do weighting by this bias, or you can do some sampling, but both of these approaches have some pros and cons. For sampling, it's probably you're just breaking your data set. It's not the same as will be running on your production. With the weighting, I have like a cool story about how we implemented inverse propensity weighting and how we shoot ourselves in the foot. So we did our perfect inverse propensity weighting ranking, and some of the e-commerce stores we were working with started complaining that for some of the search queries, or maybe some of the collections, not all of them, like 5%, so it's not significant, too many unpopular items went on the top. We started to dig deeper and found that our weighted ranking was an inverse of non-weighted ranking. So it started just to swap it for some reason. Why? Because our training data was biased towards the number of clicks. So the machine learning model, which was used to rank these items, preferred the popular items to be on the top of the list, as our propensity weighting weights it from top to bottom. So the lower the click, the more important it is. And the lower the click, the lower the popularity, the number of clicks. So it assumed quite validly that, okay, so the lower the number of clicks, the better is the relevancy. So it just swapped it, inverted it, and called it a day, because what it was asked to do it, but like implicitly, and we leaked a bias there, probably multiple biases at once, and shoot ourselves in the foot. So from the inverse propensity weighting perspective, the bias is not constant across the whole store across your website. It can be dependent on the context, dependent on the query, maybe on some list of genes, it can be high. On a list on some details for autos, it can be low. So you also need to, and you need to just spend more time estimating it, and maybe we can just instead mix it into the model, so your model can be bias aware and learn bias, relevancy, and how bias influences the relevancy at the same time. I always like to quote this PAL, position-aware paper, which is not the best way to do position-aware learning, but it's the most cited one probably. So the idea is that you have a couple of ranking factors, couple of factors in your machine learning model, maybe not about the ranking itself. Some of them are biased, some of them are non-biased. You use the whole data set for training, so it can find dependencies between the data. But on the inference side, you just fix the biased factors by some sort of a constant. So in the case of position, you just put something in the middle of the list, like, 5. And then from the model perspective, it will look like that all your items you're asking to rank are actually on the same position. And it's kind of just offsetting the bias in a way which is quite simple and applicable to not only ranking, but some other machine learning models. There is also some sort of a demo which we did with Metarank, this ranking thing with the learn to rank for mere mortals. So we have a movie recommender running on our demo website, and it's using a data set we also collected also from Toloka, surprisingly. And it's like Movie Lens, but with the ranking information. So we know what was presented to people and how they were interacting with. So people labeled favorite movies, but not like in a proper way you label movies, like, do you like this movie, yes or no? But choose favorite movies within this topic from this list. And this list is actually quite an important point because you can take the position information from there. Metarank is just a ranker, so it's usually for search, it integrates with something. For recommendations, we pre-computed everything with the ALS, because why not? And we just plugged, Metarank support this PAL with just 3 lines of code. And if why we choose PAL and not inverse propensity weighting or whatever else, because it's kind of shuffling can be costly from the business perspective. If you're learning bias together with your ranking model, it can also learn some sort of a context. And at the end, it can be also adapted not only to position bias, but you can also apply it to some other types of biases, like presentation bias. You can some sort of introduce a position in a grid if you're trying to use the grid information, or just make it aware of click-through rates or whatever. And from the results perspective, we found that introducing this position bias improves, like in DCG, slightly for 1%. Is it good? It's not the best thing you can do, but still 1% for free is always nice. So should you really debias your data in your rankings? Usually it depends. So if you have a strong navigational, strong discovery function in your ranking, probably yes. If it's not, and more about navigation, probably no. But still, you can always evaluate, just to shuffle a small subset of the data and see how people click on the same results and how behavior of people changes. You can also just see other papers which are based on PAL and see how it can be improved. But still, it's quite easy to implement. It took me like half of the day with writing the documentation, so that's it. That's the whole talk. The tool I was using for this demos is Metarank. You can hang out with us on Slack. The data set for this movie search is on GitHub. So it's open source and you can play with it. The rank lens also on GitHub and PAL paper. So that's it.
Okay, I wanted to start with online, but offline is faster. So what can I do? Okay, who was like, I'm sorry, I noticed you because of the hoodie, so I guess now you will be, yeah, you did the right thing.
Thank you. My question is about the position-aware learning. I'm not sure if they present this in the paper, but how does this approach compare to the one where you could just remove biased features from the model?
Maybe it depends on the features, but still, how can you remove position information from the model? Then I mean that there's the clicks on the first positions are not giving you much information, so you just let the model decide what is important and what is not important from the learning perspective, and not trying to do it explicitly with weighting. So it's not about the machine learning features. Probably you shouldn't use position bias position information as a feature at all in general. But you can just hint the model how important and how less important clicks on the first position. So that's the point.
Okay, I think I'll go deeper into the paper. Maybe there are some interesting notes with this regard. Thanks.
There is also, sorry, there is also a talk from the latest Haystack conference from some person from Otto. They're doing a bit deeper dive on this bias-aware learning, so you can watch that. Or I can send you a link if you come after the talk.
So this is related to the bias-aware learning part. So when you have a data set and you actually change the order, for example, your recommendations as you described at one stage, different types of people may actually react differently. So you may have an age bias, for example, that they would actually have a different, let's say, ranking for you to how to change the importance with that. There's also the kind of question that I have in the sense, have you looked at individual people, and if you look at those rankings from looking individual people, they actually give you a type of a psychological profile of how they behave by figuring out whether they are picking the first in a row or the second in a row and how they do that. So it actually contains hidden personal information that you can classify people. So this is a kind of a GDPR thingy coming on out of the system, and you can actually relate it to psychological properties when you do that.
But that's wonderful when you rank items and not people.
Yeah, but you rank items, but ranking the items actually define how people behave. I give you an example in the way in calls. If you make calls and you rank the metadata for that, so that's just the metadata is very easy thing that you answer a call and then you spend a certain time in the call. Now, if somebody calls you and you spend a long time in the phone, or then you compare it to somebody who is usually kind of spending more time than they call themselves. So that's actually defines whether you're an extrovert or introvert. It's only metadata, very high level, and you can actually psychologically profile people for that. Yeah. So this is fancy tool because now you actually, if you start changing the position on it, you actually make a psychological experiment on people.
Probably.
So this is leaking in a funny way on the system. So is there any remedy for that?
Don't try to estimate extravertal or just don't do many features which are very personal. So just for my personal experience working in e-commerce for small and medium merchants, there are not that many people coming for the second time. So you don't have a vast history of click-throughs. So it's just 1, 2, 3 interactions happening just right now. And
your answer really your eyes.
Sorry?
Your answer really is that you shut your eyes.
So yeah, so just not trying to do this cross-device or more complicated tracking and just use only session information. So you clicked on this course, because of clicked on this course, you might interested in that course. It's not related to you personally because there are no ranking features related to you, but just some sort of an aggregations. But if you go deeper with deep neural networks, who knows what goes on there? Maybe there is a special cluster, you know, for introverts.
Hey, how are you? I had a question. How is like presentation accounted for in some of these ranking, or if there's any knowledge about that? For instance, if you're on a mobile phone or different size browsers, how the presentation would change, and how kind of you can alleviate that in any way, shape, or form.
So you can estimate this bias also, just separately for different segments, or you can just So usually it is. So for the data set, this movie search one, there is also an information about the platform you did this evaluation. So it's desktop or mobile. And if you draw this probability of click per position, you can see that it's different for desktop people and mobile people. For some reason, mobile people click more. I have no idea why, but it's just decaying in a bit different angle. What to do? Probably like maybe separate model, maybe just introduce it as a biased feature. Who knows? So you just usually need to try different approaches.